Assignment 19, 3.4, derivative of the power function and another definition of derivative. All right, our essential question. Given a power function, which takes the form f of x equals some number, some base to some n power, where n is a constant or given a combination of power functions. So maybe several of them added together. How do you find f prime of x, or in other words, the derivative f prime of x? All right, let's draw my Cornell notes. This is my favorite lesson. We have been exploring what derivative means for so long, and finally you get to learn about it using calculus. Before we get there, though, I have one more definition of derivative for you. This one is the definition of derivative as a function. It comes from page 86. And so the way that it's written several ways, but I'll write it all of these ways. So f prime of x is the limit as the change in x goes to 0 of basically the slope, right? Change in y over change in x. Okay, and what then they say is, well, isn't that the exact same thing as the limit as the change in x goes to 0 of f of x plus some change in x minus f of x over that change in x. So, right, we're thinking about this as an instant, and in order for an instant to occur, time has to be 0, right? So that change on your horizontal axis has to be 0. So let me show you the graph of what they're talking about here. This is on the previous page, page 85. So they're just saying, okay, if we have some x and we add some change in x to it, right, I'm going to also have my outputs here, the corresponding outputs with those inputs. And so really, again, all we're doing is we're finding the slope, but we're finding it as that change in x is going to 0. Okay, so at an instant. And so then they even go one step further, and this is probably the one that we should use. Makes it a little bit easier to use it, and that's why they actually created this. The limit as, and now they've decided to, instead of using delta x, or change in x, they've decided to say, well, let's let delta x, or change in x, equal h. It's a little bit easier to use. So now they're just saying, well, the limit as h goes to 0, or that change in x goes to 0, of f of x plus h minus the original f of x all over h. Okay, so they're substituting delta x, they're substituting h in for delta x. You can actually take a function and you can actually find now the derivative function for that entire function. So basically it'll give you the derivative at every single point. Looking at the derivative of a power function. Now this is the exciting part. All right, so if f of x equals x to some power n, then the derivative, or f prime of x, here it is. This is what you've all been waiting for. Okay, so to find the derivative of this without getting all crazy and going into using the slope, or the limit of the slope as your change in x goes to 0, here's how you do it. Ready? You take whatever your exponent is and you bring it down. Leave your base where it is. So basically, this power just came down to become a coefficient. Okay? And then you take whatever your power was and you subtract 1 from it. And there it is. Okay, so here's your one restriction. N has to be a constant. We have more rules, okay, but right now we're just going to get you used to using calculus, and this is actually using the calculus. How exciting. It's so easy. Wait till you see it. You're going to be like, why did you make me do all that work? We made you do all that work so that you could explore what the meaning of derivative actually means. All right, so here's an example. I have f of x equals 3x to the 5th plus 2x squared plus 7x plus 5. All right, so let's find the derivative of f of x, or f prime of x. All right, so these are all powers. Okay, so I can basically take my power and bring it down. Now, if there's already a coefficient, then you're going to want to multiply those two together. So I'm going to end up with 15, keep your base, and then subtract 1 from your power. Wasn't that easy? Okay, and we can keep going. So now I'll do it to the next term. So bring the 2 down, multiply it to the coefficient that's already there. So that's 4, and then x, and then you want to subtract 1 from this, so it's just x to the first power. Okay, next term. So what's the power right here? That's right, it's 1. So when I multiply that by 7, I just get 7. And then this becomes x to what power? That's right, x to the 0 power. So do I have an x anymore? I don't, because x to the 0 power is just 1. And you're in calculus now, so it's time for you to know that. X to the 0 power equals 1. Anything to the 0 power equals 1. All right, let's do our last term. So now I have x to the 0 power here, right? Because there was nothing there, or there was a 1 there. So what happens when I bring that 0 down and multiply it? The whole thing goes away, right? So now I have nothing, all right? So whenever you take the derivative of a constant, think of it, right? There is some variable there, or some base there with a power of 0, and you're just multiplying that constant by that 0. It's not there anymore. So this is our derivative. Okay, I'm going to flip my paper over because our next example that I'm going to do is quite lengthy. So we are going to work on an example. It's from page 90 and it's number 22. So for these, we have a few things we need to do. We need to use the definition of derivative in the form of f of x plus h form to find the equation of the derivative function. And then in each of these cases, so you'll end up doing the odds, show that your answer is consistent with the answer you would get if you use the formula for the derivative of the power function. Okay, so we're going to do number 22, s of t. All right, so we'll start out by using definition of derivative. So that's going to be the fact that the derivative, or s prime of t, will equal the limit as h goes to 0. And it's going to have s of t plus h minus s of t all over t plus h. Well, sorry. If I do t plus h minus t, I'm just going to end up with h. I was just looking at the inputs there. So h. It's hard for me, instead of memorizing, something like this, I remember that my input's t plus h. And so then I would just take t plus h minus t, and I end up with just h. So that's where I was going with that. All right. So now I'm going to plug everything in that I do have. So this will be the limit as h goes to 0. Now, everywhere that I see a t, remember my input is t plus h. So this is going to be t plus h to the 4th power minus 6 times t plus h squared plus 3 point, I copied it wrong. It should be 3.7. 3.7, that was going to really mess us up. And then from there, I just subtract the function where my input is t, which that's just that. So t to the 4th minus 6t squared plus 3.7 all over h. Now I can't just plug 0 in, because if I do that, it's going to be undefined. Okay, so I need to figure out a way to work with this. All right. Here's my problem. Look at what I got here. T plus h to the 4th. Oh my goodness, who remembers how to do that? Well, you have a couple of options. Okay, I'm going to come up here. So, t plus h to the 4th. Well, isn't that the same thing as t plus h times t plus h times t plus h times t plus h? Great. I can do that. That's going to take a long time. Another thing I can do is I can think about binomial expansion, and I can use the Pascals triangle, which is my preferred method. So here's what I'm going to do. Pascals triangle. You can always create this, right? You start with 1. Okay, on the outside here I've got 1s. Now I'm getting to my 3rd row here. I add whatever's above. Always along the outside you're going to have the 1s. Now I care about the 4th power, okay? So the top row is always the 0 power. Next row is the 1st power. Next row is the 2nd power. Next row is the 3rd power. So I need one more in order to get to the 4th power. And again, I'm just adding the tops and putting 1s at the end. So this is the 4th power. Okay, this tells me what my powers are. So here's my pyramid though right here. So in the 4th power, this is going to tell me what my coefficients are going to be. Okay, so I'm going to use this right here to help me expand this binomial. Okay, so the first coefficient is going to be 1. And my first variable is basically going to be t to the 4th. It's really t to the 4th, h to the 0. Okay, and as I continue along, I'm going to drop the power by 1 of t, and I'm going to increase the power by 1 of h, so that they always add up to a total of power of 4. All right, so next, my second term is going to have this coefficient. And if you don't believe me, go ahead and multiply this all out. I encourage you to. It's fun. Why not? I'm sure you got plenty of extra time. Okay, so 4. Now I'm going to have t to what power? The 3rd power, right? And then h to the 1st power. Plus, okay, and now I'm going to use my 6. 6. T to what power? Good job, 2nd power. H to what power? That's right, 2nd power. Okay, next term, what's going to be my coefficient? 4. T, H to the 3rd power. Oh, you guys are getting the hang of this. All right, and then my last term, coefficient of 1, T gets 0, and then H will have 4. Oops. Now I am going to so run out of room right here. That's okay though. All right, so next for this, I'm going to have minus 6, and that happens to be, I can do this in my head, t squared plus 2th plus h squared. Okay, I need to add, let's see, how do I want to do this? I'll add 3.7, and then I'm just going to distribute my negative here. Minus t to the 4th plus 6t squared minus 3.7. Okay, well that's a disaster. We've got a lot of stuff going on there. So now I have to work on simplifying this. Right away I can see that I have a t to the 4th and a negative t to the 4th, so I'm just going to get rid of those to begin with. Do I see anything else that cancels out? Oh, and all of this was over h. And I got so excited about binomial expansion, I forgot to write this is the limit as h goes to 0. Okay, so I'm going to drop down, I think, one line. Give myself a little bit more room to work. Okay, do I see anything else that is simplifying? Not so much yet. So I'm going to write down what I have left. And I need to use proper limit notation. So this is, again, the limit as h goes to 0 of 4t cubed h plus 6t squared h squared plus 4t h cubed plus h to the 4th minus 6t squared minus 12th minus 6h squared. Oh, I do see something else that reduces. You probably already caught it. Positive 3.7, negative 3.7. So I think I've just got a plus 6t squared left. And all of that goes over h. Okay, I see some more stuff now that can reduce. The negative 6t squared, the positive 6t squared. I'm going to say that's it. Now, I'm wondering, does everything that's left have an h in it? Right, because it's kind of important that I get rid of this h, because it's kind of hindering my ability to take the limit. So I see that every single term has an h, and I'm going to factor it out. Factor out the h, I'm left with 4t cubed plus 6t squared h plus 4th squared plus h cubed minus 12t minus 6h. Yay, so I finally have a way that I can reduce out those h's. Okay, and now my final answer, I can go ahead and I'll plug 0 in everywhere that I see h, and let's see what happens. So 4t cubed is going to stay. But when I plug h in here, what happens to it? It becomes 0, right? So this next term's gone. This next term's gone. This term's gone. I got a negative 12t. And that term's gone. Voila, there it is. Whew, that was a lot of work. All right, let's see if we can do this a different way. So now let's take this, and let's actually just use the derivative of a power so that we can actually just do this really quickly. Ready? I'm just going to do it up here. Taking the derivative. Okay, so I take my power, I bring it down, multiply it by this coefficient, and then take 1 off of it. Okay, now I'm going to take this next term, do the same thing. Now there's a negative 6 here, so when I multiply, it's still going to be negative 12, t to the first power. And then the derivative of a constant is just 0. Voila, I'm done. Notice how those two match? Wow. Which one do you prefer? Probably this one, right? Haha. It's late. I must be tired. All right. Couple of other things I want to go over. Actually, I'm going to go back up to the front because we have some space here. And if you don't, you can put this anywhere. Let's talk about derivative notation. Okay, so a few ways that we can write this. You already know that f prime of x is one way of writing the fact that we're taking the derivative of x. Okay? But other ways that you're going to see this, I can say, well, this is the same thing as, this is an operator now. Taking the derivative with respect to x. So this is, I'm taking the derivative with respect to x of some function. Maybe that function is f of x, right? Because this is f prime of x. So this is like an operator, like imagine like it's like a multiplication sign or something, okay? This is saying take the derivative with respect to x of f of x. Okay, I'm going to use this notation a lot. So while this is really easy, and a lot of times you'll see it in your book like this is our preferred method. Okay? Another way that we can write it, so let's say, for example, your function was not called f of x, maybe your function was called y, right? Kind of like how we first learned how to deal with equations. Well, when I take the derivative of y, that's really the derivative of y with respect to x. So that's just like this, right? This is the derivative of f of x with respect to x, or the derivative with respect to x of f of x. This is the derivative of y with respect to x. Okay? So these are, oh, sorry, and it would be y prime. So you can write it as f prime of x or y prime. Now, again, a lot of you guys are going to want to use this y prime or this f prime of x. This is the better way to go because we're showing that we're taking the derivative of something with respect to x. And what we're going to end up having to do are these like crazy chain rules where you're going to need to show, hey, I'm taking the derivative of something with respect to something else. Okay? You're going to need to know how to do this. And there's another word that's slipping my mind right now, but I'll talk about it probably in a future video where we're going to need to do this. All right, so the way that this says, that this would actually be said, is that this is the derivative of y with respect to x. Again, I'm going to make a big deal about these, okay? Don't say, oh, that's just too confusing, I don't want to use those, and stick with these, okay? There's a time and a place for everything, but you're going to, implicit differentiation, that's what it is. When we get to implicit differentiation, if you're not familiar with these, it's going to get really complicated, okay? Because we're going to have all kinds of variables and all kinds of functions that we're going to be taking the derivative of. All right, there are some differentiation properties on page 88. So differentiating means to take the derivative. Differentiation properties They're on page 88. Some are more important than others. So, let's see. I expect you to know these. I'm not going to write these all down for you because they're right here. Okay, but basically if you have a function that is composed of two different functions, and both of these are differentiable functions, then you basically just take the derivative of each of these functions separately and add them together. Okay, or, think of it like if you have two terms, you can take the derivative of each term separately. Just like we did right here. Our first example that we used the derivative of a power function, right? Each of these terms, we were able to take the derivative of them separately and keep adding them together. Okay? All right, so derivative of a constant times a function. This is an important one, and I am going to write this one down. So derivative of a constant times a function. So if you have the fact that f of x equals some constant or coefficient times g of x. All right, so what happens is when you take the derivative, the constant doesn't change at all. Not at all. Okay, the constant remains there. So this is going to be the constant stays, and then I take the derivative of whatever it's being multiplied to. So an example of that is if, let's say, f of x equals 5 x squared. Okay, so if I take the derivative of this, you have to remember nothing changes to this. This stays. Okay, and then I take the derivative of this piece right here, which is really me just bringing down the 2, keeping my base, subtracting 1 from this 2, okay, which basically just gives me 1 here. So this ends up being 10x, but I haven't changed that constant at all, okay, or that coefficient. It just happens to get being multiplied. Okay, but then the last one here, and I am going to make a big deal about this. This is one of the easiest things, and I don't want you guys to get messed up on this. So if you have the derivative of a constant, so let's say I have f of x equals some constant c. Well, when I take, okay, so let's think about that. So a constant function is just some like y equals something, right? So let's just call it some straight line here. Okay, so this is x, this is f of x, right? So let's call this, y equals 1, or f of x equals 1. Well, what's the slope on this? Right? Because that's basically what finding the derivative means, right? You're finding the slope of the tangent line at some point. Well, no matter where I draw a tangent line, my slope is going to be 0, right? Any point here, if I try to draw a tangent line, I'm just going to have a horizontal line. So my slope ends up being 0. So that tells me that if I try and take the derivative of a constant, I get 0.